Welcome to Visual Algebra Lecture 5.2, 5 Features of Group Actions. Every group action has 5 fundamental features that are worth trying to understand: orbits, stabilizers, fixators, the kernel, and the fixed points. The first 3 of these are local, in that they depend on individual set or group elements, and the last 2 are global. They depend on the homomorphism that defines the action. Several of these are dual to each other. For example, the stabilizer of a set element are the group elements that fix it, whereas the fixator of a group element are the set elements that it fixes. The fixed points are the set elements fixed by the entire group, and the kernel are the group elements that fix the entire set. If it's hard to keep track of this, no worries. It's incredible at how the group switchboard analogy and the action graph visual can help. We'll also see a new visual in this lecture called a fixed point table. This is one of the most important lectures of this chapter, and I really think that everyone taking abstract algebra will benefit from it. So let's get started. Before we get started with this lecture, I want to recap some of the key ideas from the previous lecture. Please go watch that video if you have not already. So a set S with an action by G is called a G set. Now, why do we bother defining this if we already have the definition of an action? Well, here's why. So an action, recall, is a homomorphism from a group G to the permutations of a set S. And this endows S with an algebraic structure. And here's my favorite example of this, where D4 acts on this set of 7 so-called binary squares in the obvious way. When you press the R button, so this is a group switchboard analogy that I use, and every time you press a button, things get moved around, permuted. So when you press the R button, then everything gets rotated 90 degrees counterclockwise. You follow the red arrow. When you press the F button, everything gets reflected across a vertical axis. You follow the blue arrow. And then the key property here is that when you press the R button and then you press the F button, that's the same thing as pressing the RF button. And that's why it's a homomorphism. Now, what I've shown you here is the action graph, and this is like a generalization of a Cayley graph. But the G set is the actual set of size 7 that has an algebraic structure on it. And the algebraic structure is basically this group switchboard with these arrows that tells you what happens when you apply a group element to this set. So if you use a different generating set, so this is D4 generated by a rotation and a reflection, but you can generate it with 2 different reflections. So this reflection S is across a diagonal axis like this, and whereas F or S is across a vertical axis. So notice how changing the generating set, just like for Cayley graphs, will change the actual action graph, but the underlying algebraic structure is not dependent on the choice of generating set. So when you do the R button, press the R button and then the F button, you go from, say from here, you go RF, so you go from this square to that square. But down with this generating set, that's from this square to that square is down there. That's because red, blue equals green. Pressing the R button times the F button is the RF button. Okay, so that's what we're going to work with. And these groups that I put here, these are what I'm going to define to be the stabilizers. These are the paths that are loops that start and end up back here. So R squared F is a loop here, F is a loop here, R squared is a loop here, as is RF, as is the product of these, R cubed F, and of course the identity. As said in the title and the intro of this lecture, every group action has 5 fundamental features that we will always try to understand. And there are several ways to classify them. 3 of them are subsets of the set S, and 2 of them are subgroups of G. Another way to distinguish them is by local versus global. 3 of them are features of individual group or set elements, and we will write these in lowercase. I'll show you what I mean shortly. And then 2 of the features are attached to the homomorphism phi, and we will write these in uppercase. We will see parallels within and between these classes. For example, two local features will be dual to each other, as will the global features. Our global features can be expressed as intersections of our local features, either ranging over all set elements or over all group elements, depending on the definition. We'll start by exploring the three local features first. Throughout this lecture, we will have two different groups. We'll have the group G, which is the domain of the action, and then the permutations of S, which is the codomain. And both of these have an identity element, and just to keep them straight, I will denote the identity element in G by 1 and the identity permutation by E. We'll start with two local features, both of which are defined for individual set elements. Suppose G acts on a set and picks some element S in the set big S. We can ask two questions about it. First, what other states in big S are reachable from our element S? We call this the orbit of S. Next, what group elements, that is in G, fix S? We call this the stabilizer of S. Let's define this formally. Suppose that a group G acts on a set, let's say it's a right action, via a homomorphism phi from G to the group of permutations of the set. The orbit of an element S is the set that I will denote ORB of S. Notice the lowercase o because this is a local feature, and it is the set of S dot phi of G where G ranges in the entire group. The stabilizer of S lives in G, and I write that stab of S, again lowercase s, that is the set of all group elements, little g, such that S dot little g is equal to S. Even if you can understand what these things mean intuitively, it's important that you can translate that into a nice set builder notation definition like this. I've definitely seen a lot of gaps where people understand what this is, but then they have trouble writing it up formally. And that's something that you learn in your Intro to Proof course, but you develop and hone in this course. And you won't be able to do proofs if you can't write down the definitions. It's always a good idea when we learn a new definition in group actions to try to interpret it in terms of our favorite visual, that is the action graph, and also in terms of our favorite analogy, which is the group switchboard. We'll start with the action graph. The orbit of an element S is just the connected component containing it, and the stabilizer of S are the group elements whose paths start and end at S. I call those loops. So let's do a very quick sketch of an example. So in the previous lecture, we had a size 4 component. Let me just briefly, I'll call one of these nodes S and the other one S prime. And we had a 4 cycle like that. Then we had a blue loop here, a blue loop there, and a blue edge like that. So this orbit containing, or the orbit of S is just these 4 nodes. And then the stabilizer of S, well, contains the identity, just the path that does nothing. And it also contains F, which is this loop. But it also contains R to the 4th, but that's F, and also RFR, which is also F in D4. Remember, RFR equals F. That's one of those relations. So the stabilizer of S is just the subgroup generated by F, but that's not the stabilizer of S prime. So F is not a loop from S prime, but R squared S is. So the stabilizer of S prime is R squared F. We'll do some more examples of this shortly. Our first 2 local features, the orbit and the stabilizer, were specific to a certain set element. Our last local feature is defined for each group element G. A natural question to ask is, what states in S does the element G fix? Here's a formal definition. Suppose that a group acts on a set, also say it's the right action, via a homomorphism phi from the group to the group of permutations of the set. The fixator of an element G are the elements in the set that are fixed by it. So that is fix of G, again a lowercase f because this is a local feature, is the set of little s's in big S such that little s dot phi of G is equal to S. In terms of the action graph, the fixator of an element little g are the nodes from which the G paths are loops. Even though I'm a big advocate of action graphs, I like the group switchboard analogy even more, at least for these definitions. So let's interpret our three local features in that setting. So again, we have a group switchboard up here. The identity has a button. A has a button. A inverse has a button. B has a button, and so forth. There's a G button, etc. The orbit of a set element S are the elements in S that can be reached by pressing some combination of buttons. So we have some little s here, and if S prime is in the orbit, that means there's some way to get from S to S prime by pressing some buttons. The stabilizer of S consists of the buttons that have no effect on it. So if G is in the stabilizer, that means when I press this button, we stay right here. S doesn't move. The fixator of a group element, G, are the elements in the set that do not move when we press the G button. So for example, if this is green, say, and then S is in the fixator, if when we press the green button, it's a loop. We don't move. Now, I want to make some comments about this. First of all, though this group switchboard analogy seems like a learning or training tool, I use it to this day. I find it incredibly useful when I have to keep track of stabilizers and fixators and which one is fixing what, etc. That's one thing. The other thing is the notation that I've been using. Let me remind you, the orbit I call ORB of S. The stabilizer is stab of S, and the fixator is FIX of G. Again, I like to use lowercase because these are local features. I don't know any other source that does that. I think some sources use stab, but I more often than not see capital S and often a capital O as well. That's one thing. Another thing is some books call these things or use different words. So I think the orbit is pretty standard, or words and or notation. So the orbit is pretty standard for terminology, but in terms of the notation, some books will write, and this is not terrible, G dot S or S dot G, depending on whether or not we're talking about a left action or a right action. So for a right action, we would use, or a book would say S dot G, because it's all things that you get. It's like coset notation by starting with S and then multiplying by something in G. So this is not too bad, but there's similar notations for stabilizer and fixator that I really don't like. For the stabilizer, some books like to write G sub S. So that is the group G and the element little s. And then for the fixator, some books will write, to make sure I had this right, S to the G. And I don't really like this at all because we're going to see a couple of theorems involving orbits in the next lecture. And if you look at these on Wikipedia and a lot of books, they involve an equation with S dot G and G sub S and S to the G. And that's just confusing. It's hard to keep track of which one it is. Maybe if you do this every single day, but I think it's just much easier to write orb, stab, and fix. Finally, I should say that some sources use different terms for these concepts. I think orbit is pretty universal, but stabilizer, well, this will be a subgroup. So sometimes it's called stabilizer subgroup, but other books call it the isotropy subgroup. And I've even seen the fixator, and I really don't like that at all because fixator means something else. But I think stabilizer is the most common. And then for the fixator, this isn't as common of a feature to study than orbit and stabilizer. So some books just call it like the fixed set of G or the fixed point set of G, something like that. I don't like that because one of our global features is going to be a set of fixed points. So I don't like having those two things, a fixed point set and set of fixed points together. And I tried Googling it and I don't find very many books that call this the fixator. I did see one recently that did, and I have a number of students who are Francophone, and they tell me that fixator, spelled a little differently, F-I-X, I think, A-T-E-U-R, is commonly used in French. So I'm going to stick with fixator. I don't have a better alternative than this. Let's now return to our running example from the previous lecture. Please watch that if you have not, and understand what the orbits, stabilizers, and fixators are in that. So for this one, the group D4 acts on a set of 7 so-called binary squares, and here's the action graph. Pressing the R button rotates things 90 degrees counterclockwise, and pressing the F button flips it about the vertical axis. So there are 3 orbits. These are the connected components. Then the stabilizers, I'm writing that group by each node. So we already went around these two, but the stabilizer of this is, well, red, red, R squared, red, blue, R, F, and then the product of these is R cubed, red, 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 blue, and then the identity. So that's the stabilizer of both of these things, and the stabilizer of D4 is everything. What about the fixators? So when I press the identity button, everything stays fixed. When I press the R button, well, everything's going to move except this all zeros thing. And same thing with the R cubed button. Let's do the reflections next. When we press the F button, well, we can see that that's going to fix this one and also these two. We can see that loop. So the fixator of F contains 3 squares. And then what about RF? So RF, when we press that button, this is so let's make that one green. And so this corresponds to a reflection across this axis, and that's going to fix these 3 things right here and none of these. But also R cubed F, which is the reflection across this other diagonal axis, will also fix those. And also R squared, the 180 rotation, is going to fix these 3 things as well. So the fixator of all 3 of these elements are these 3 squares. And finally, R squared F, that's fixed by these 2 things here and that. At this point, I want to introduce to you a new visual that I really like a lot, and I think you will too. I call it a fixed point table. So I'm going to put the group elements along here and the set elements along here, and anytime that there is a group element that fixes a set element, I'm going to put a check mark right there. So the identity fixes everything. R is only going to fix this guy. R squared is going to fix the 180 rotation fixes these 3. And remember we said that RF and R cubed F will also fix those. So we put checks there. R squared X is going to fix this one and also those 2. And then F will fix this one, that's the vertical reflection, and these 2 as well. And then R cubed is like R. So notice that the stabilizers can be read off of the columns. So if I want to know what stabilizes this set element, I just look down and say, okay, at which group elements are there check marks? So we can read off the stabilizer of any element just by looking at the column. And then the fixators can be read off of the rows. So if I want to say what Set elements are fixed by the 180 rotation r squared. I just look at which columns there are check marks in, and that tells me what the fixator is. So this row by column thing is what I like to say. It describes what I mean when I say there's a duality between two of our local features. So in linear algebra, dual spaces you can think corresponds to taking the transpose of a matrix, swapping rows and columns, and that's kind of what we're doing here. But also there's a duality just in the English language. We say the stabilizers are the group elements that fix a certain set element, and the fixators are the of a group element are the set elements that it fixes. Notice how in our examples, thus far, the stabilizer of each set element is a subgroup. This holds true for any action, and it's fairly straightforward to prove. Let's do an outline right now. For any set element S, the stabilizer is a subgroup. To prove this, we have to show that the stabilizer satisfies the three properties of a subgroup. Associativity is inherited from the operation, so we just have to show that it contains the identity, that it's closed under inverses, and that closure under multiplication. So let's first talk our way through these using the group switchboard analogy. Why does this contain the identity? Well, we have this switchboard, and there's an identity element, and the stabilizer contains the identity because whenever we press the identity button, we get the identity permutation, because phi is a homomorphism from G to the permutations, so it must send the identity element in G to the identity permutation. So pressing the identity button will fix everything, including S, so that makes sense. What about inverses? So if we press the G button and we fix S, so that means S is something like this, and we press the G button, maybe that's some path, but it's a loop. Well, then why does pressing the G inverse button also stabilize S? Well, the G button means you follow the G path, and the G inverse button means you follow it backwards. And so if one direction is a loop, the other one is as well. So this makes sense. And then finally, under closure, so if we have two, maybe I should be doing calling these A and B, but let's call we don't have an H in here, so let's say we have an H button, and H stabilizes S. Well, that means that there's some loop, or if we follow the path corresponding to H, it's a loop. So closure just means that when we press, if G and H both fix S, then so does GH. So when we press the GH button, I mean, that's the same thing as pressing the G button and the H button, because phi of GH equals phi of G times phi of H. In terms of paths, that means if G is a loop and H is a loop, well, then so is the concatenation GH. Okay, let's actually prove this. Why does the stabilizer contain the identity? Well, S dot G of 1 equals S, because what I said up here, because phi of 1 is the identity in permutation. Homomorphisms send identities to identity. What about inverses? So let's say that S dot phi of G equals S. And we want to show that S dot phi of G inverse equals S. So how do we do that? Well, S dot phi of 1 is S, that's equal to S, right? We just did that. But that's also equal to S of phi G inverse. This is S dot phi of G times phi of G inverse. And this thing, because G fixes S, this is equal to S dot phi of G inverse. That's what this entire thing is. And that's equal to S. So in other words, we know the identity fixes S, and we know that G fixes S, so this must be S, so G inverse must fix S as well. And then what about closure? This one is also kind of one of those follow your noses. So let's say that S dot phi of G equals S, and S dot phi of H equals S. So in other words, G and H are both in the stabilizer. Why is their product in the stabilizer? Well, then S dot phi of GH, just follow your nose, S dot phi of G times phi of H. And again, this thing here is equal to S dot phi of H. And we know, H is in the stabilizer, so this is equal to S. And that's all we had to show. As we've seen, elements in the same orbit can have different stabilizers. However, there is some structure here. I claim that set elements in the same orbit have conjugate stabilizers. And specifically, the stabilizer of S dot phi of G is equal to G inverse times the stabilizer times G. So this is a conjugate subgroup to the original stabilizer. Now, what is this really saying? It says that if X stabilizes S, that is, if S is the stabilizer for S, then G inverse XG stabilizes S dot phi of G. So to prove this, this can be done just by proving both directions, both this containment and that containment. But I like to be able to understand why this is true before we just try to do some, use the definition and plug it in. And this is one of the examples where the action graph really makes it apparent for why this should be true. And I'm going to start with the action graph version over here. So suppose we have S, and then we hit the G button and we send it to S prime. So what this is saying is that if X stabilizes S, that means that X is an element that has some path that is a loop from S. So anytime we have a loop corresponding to pressing the X button from S, then we have a loop, a different loop from S prime. Do you see it? First, do the G inverse path to get you to S, then do X, and then do G again. I'll say that one more time. If X is a loop from S, and then G gets me to S prime, then starting from S prime, G inverse X, G is a loop from X prime, S prime. So if X is in the stabilizer, G inverse X, G is in that stabilizer. That's all this is saying. That's all this is saying. Here's two other ways to see it in terms of these so-called binary hexagons. If I take this hexagon and I flip about the vertical axis, and that stabilizes this, well then if I can let's rotate this by 60 degrees. We rotate both these by 60 degrees, then what stabilizes this? This is, I'll use blue as well, the reflection across this axis. So again, if we can write this thing here if we want. I can write this as if F fixes this, and then we go R here, then R inverse F R, and by the way, R inverse F R equals R to the fourth F. That is going to fix this one. So here having this here, this is almost like a copy of both of these things. It's like a pulled out version of this, but it is nice to have a commutative diagram. It means if you press the X button and then the G button, that's the same thing as pressing the G button and the G inverse X G button. Now, do you see why that is true? Because what happens when you press, so you start with Up here, you start with S, and then you press the phi of X times phi of G button, and that gets you from there. But if you go the other way, well, S phi of G inverse X G, that's going to give me the same thing because you move these inside and the G's cancel, XG and XG. So that's what you get this way. So this is a really good exercise to do. I think I actually might have it in my book. So when that comes out, you can check it out. But here's also 3 different ways to motivate really why this is true. This one's my favorite, but it is worth pulling up your sleeves and getting your hands dirty and really understanding these 2 things as well. Here's another example of an action or a G set that I will return to in this chapter as well. This time the group is the dihedral group D6, and our set consists of 6 so-called binary hexagons, these 6 right here. So let's let S be the little s be the highlighted hexagon, and let's denote the stabilizer by H. Here's what I want you to notice, and this is going to be a little bit of a preview into the next lecture, and that is that there is a bijection between cosets of the stabilizer and destinations, other places in the orbit. So H are precisely the set of paths that when you start here and you follow them, you end up here. But if you want to end up here, then you have to do something in H, some loop, and then do R to get you here. So that's the coset of paths HR. To get here, you do so, you can dally around and do all sorts of things. As long as you end up here, you're staying in the stabilizer. And now you got to do R squared to get here. Or some other element in the coset. This coset contains R squared. It will also contain R, R squared F, R, F, R. Each of these cosets is size 2. I don't know if the thing I said was R squared or not. And then again, to get here, you got to do some loop and then do R cubed. Here, some loop, and R to the 4. So there is this bijection between destinations and cosets of the stabilizer. Over here, I'm labeling these nodes with the stabilizer. So the stabilizer of this is generated by F. So what's the stabilizer of this thing up here? Well, do R inverse F R, and that is R to the 4th F. And you can see that. That's another way to see that is R to the 4th F, which is equal to R inverse F R. What about this one? What's a loop here? It's got to be a conjugate subgroup to this, so it's got to have 2 elements. So it's the identity, but also R squared F, which is the same as R minus 2 F R squared. This stabilizer is F. This one here is R to the 4th F is a loop. R squared F is a loop. These are all conjugates. So this is what we just saw, and I think it's worth putting these side by side. It will give you intuition about what's coming up in the next lecture. Okay, so we've spent most of this lecture on our 3 local features, but we have 2 global features of every group action, and those are the fixed points and the kernel. So I call these global because they are properties of the actual action, that is the homomorphism, rather than of specific elements in the group or the set. One of these definitions, fixed points, is new, and the other one, kernel, is a familiar concept, but in this new setting. Suppose that G acts on a set via a homomorphism phi from G to the set of permutations. Well, since this is a homomorphism, it has a kernel. The kernel of the action is just the kernel of the homomorphism. One reason why I like the homomorphism definition better than the one that we saw at the end of the first lecture, which is G cross S to S with certain properties. And the kernel of the action is the set of all elements in the group that can map to the identity permutation, which we can write as the set of elements in the group K such that S dot phi of K equals S for all elements S in the set, Either of those is fine. The fixed points of the action, which are denoted fix of phi, are the orbits of size 1. So the fixed points is the set of all elements S in the set such that S dot phi of G equals S for all group elements. Once again, I use capital letters for kernel and fixed points because these are global actions. And that's why I use capital K for kernel in general in my book. And most books use lowercase k. I do it because of the group action, the consistency that I want. And this is why, I don't like calling fixators fixed point sets, because there's the fixed points and the fixed point sets. That's just too confusing. Here's a proposition. It's more just a remark than something we have to prove, but there's a global duality between the fixed points and the kernel. So suppose that G acts on a set via this homomorphism as before, then the kernel of phi is the intersection of all the stabilizers, and the fixed points are the intersection of all the fixators. And let's think about why that is. So the stabilizer are the group elements that fix these individual set elements. Well, the kernel are the group elements that fix everything. So we need to intersect all of the stabilizers, and that intersection are the things that fix every set element. That's the kernel. And the fixed points of the action, these are, so remember what the fixator is. The fixator of little g is the set elements that when you press the G button, nothing moves. And so the fixed points are the things that when they don't move when you press any of the G buttons. Since I've defined the kernel and the fixed points and used uppercase letters, I also want to define orb of phi for the set of orbits of the action. So I don't call this the sixth feature because it really is the set of, we've defined orbit, and this is just the set of all the orbits, but there will be a theorem in the next lecture that where I do want to speak of the set of orbits, and namely how big it is. So I will use this notation occasionally. As before, we will get a lot of mileage out of going back to our action graph visual and group switchboard analogy and interpreting these concepts there. So here's our favorite running example. And the kernel of phi are just the group elements whose paths are loops from everywhere. So R is a loop from here. F is a loop from here, here, and here. R squared is a loop from here, but not from here. And you could check 8 of these buttons, and every single one of these buttons moves something except for the identity. So the only path that is trivial from every node is the identity, which you can think of as doing nothing, or you can think of as F squared or R to the 4th, or so forth. The fixed points of phi are just the size 1 connected components. That's easy to see. This is a fixed point because it's a size 1 component. As before, I still prefer the group switchboard analogy. Well, except for the fixed points is pretty easy to see this one. But the kernel of phi, it's just the broken buttons. It's which buttons, when you press it, does nothing move. So remember, our action is defined via a homomorphism from G to the permutations of S. And so so when I press, the homomorphism is when I take a button and I press it, what permutation do I get? So when I press the identity button, nothing moves, and that button is broken. But none of these other buttons are broken. When you press them, something else is going to move, so the kernel here is just trivial. And then the fixed points of this are the set elements that are never moved by pressing any button. So you can hit these buttons as much as you want, and if you do that, sometimes this will move over here, this might move over here or something, but this will never move no matter how you press any of the buttons. Finally, let's look at the fixed point table and interpret these concepts there. Remember that we could read the stabilizer of a set element by just looking down the column. and the fixator of a group element by looking across the row. The fixed points consist of the columns where everything is a check mark. These are the set elements fixed by everything. So fixed point, there is our fixed point because there's a check mark everywhere. And dually, the kernel consists of the rows where there are check marks everywhere. So these are the group elements that fix everything. And here you can only see one of them. So this is, again, why these two concepts are dual. You just take the so-called transpose of this table, interpret rows of one versus columns of the other. And I think that's a good place to stop. So in the next lecture, we will see two really important theorems about orbits. And one of them is going to tell us how big an orbit is in terms of its stabilizer. So generally, the more things that fix a set element, the fewer destinations there can be, and the smaller the orbit is. But this theorem will quantify that. And then the other theorem is going to quantify how many orbits there are. So loosely speaking, the more check marks a table has, the more random button presses will not move things. So the more fragmented the diagram will be, and the more orbits there are. So we can also quantify this with a formula as well. Okay, so that's a lot of fun. It's also a really important thing for this lecture. Make sure you don't miss it. I'll see you then.